Okay. Just a quick review first. Okay. Last lecture we started talking about welded joints. The first case, the welded joints, we're focused on the fillet weld, and the case we're focusing on is the F is in the same plane as the weld group. So this is the weld group here, and this is the F at here. So F in the same plane at this. So we call this as in plane case, right? Yeah. So when it's in plane, what we need is we need to figure out the critical location on the weld group. Typically what you need is you need to know the geometry, basically what the geometry of the weld group is. It could be too vertical, to be too horizontal, or it could be shaped like this, right? So free body diagram tells you, okay, the force and the torque acting on the weld group, okay, are centered at this centroid here. And there's the shear force, which is the same quantity as F at here. Okay, there's also a torsional. There's also a torque generated by the F. Okay, so that's F multiplied by the distance to the centroid. Okay, so those two are the external loading, and based on these two external loading, then you can find out where the critical location is. Right, and so for the torque, apparently where the location has a largest distance, and you will have the largest torsional shear stress, right? So that's why we look at this location here. We have this so-called primary shear, secondary shear, and then combined, it's the shear stress. Okay. Once you have the shear stress, then we'll be able to deal with the safety of this one. Okay, I'll show you in an example here. But the first is we have to figure out what's the maximum shear stress at the critical location there. Okay, and that's for the in-plane case. Okay, this is for in-plane. Okay. So today let's talk about the second case, which is called out-of-plane. So case number 2. Okay, out-of-plane here. So what do we mean by out-of-plane at here? Is I'll grab the picture first. So this is an out of plane situation in here. Okay, yeah, this is out of plane. Now, if you look at this one, as I said in the last lecture, I need you to establish clear distinction between this out of plane and in plane here. Okay, so when you're given the question, if you mixed up the in plane and out plane, you know, basically the whole question is 0%, right? Doesn't matter how accurate you can calculate it. So in this case, why do I call it out plane? Because this F at here, compared to the weld group at here, they are not in the same plane. Okay, they're not in the same plane. So the weld group is here. Okay, so maybe too horizontal, maybe too vertical, and the force is over here. So basically, the plane formed by the weld group is not the same in the same plane as where the force is applied here, right? Not like the previous one. See, this is a plane forced by the weld group, and then the force is right here, so that's in plane, right? And now the force is here, so that's out of plane. Okay, yeah. And if it's out of plane, and we do the same approach, so let's have a free body diagram first, okay, and then look at the critical location of the weld group, right? Okay. So in this particular case, a symbol like this basically means you have a weld on both sides, okay, of this T-bar right here. Okay, when you do a free body diagram, and there is a shear force and a bending moment to balance this F right here, right? To balance the F. So basically, at the weld group right here, okay, at the weld group, there are going to be two different kind of a stress. One stress is caused by the V, and the other stress is going to be caused by the M at here, right? Now, the V, that's kind of easy to understand. So basically, what you do is, okay, so let's say you pick a point, okay, on the weld group. Now, where do we pick the point then? Now, if you remember in the previous lecture, when we analyze welded joints, so what do? We use a conservative model, right? And that conservative model says we only look at where? Only look at the throat area, right? The throat area. Basically, you only look at this area here, okay? This area. So basically, you can pick any point, you know, at somewhere over here. So just for illustration, right? But you need to understand that the point that you picked, okay, is on the throat area, okay, on throat area here. So there is going to be a shear stress caused by the V. Well, V, this is balance here, but if you cut a cross section right in front of it, then there is going to be a shear. There's going to be a direct shear, not a direct shear. There's going to be a shear stress, right? The shear stress caused by the V there. So that's what we call the primary shear, just like the in-plane case. So first, primary shear. We still use a tau prime for the primary, and that equal to V over A, so basically F over A. And what the A here represents is the area of, this is basically the total throat area, or the area of the total welded area, okay? Yeah. And that, if you recall that we use a table to find this A, or you can just use a hand calculus, okay? And same thing, well, I'm going to show you the table just shortly, okay? So this is the total, okay, throat area, okay, yeah, and that's tau prime, okay, that's tau prime there. Now, second kind of a stress is going to be caused by the bending moment, okay, bending moment here. So the bending moment, technically speaking, we learned the bending moment causes what kind of stress? What do we call that? What's the name of the stress caused by the bending moment? First lecture reviewed. It's called bending normal stress, right? Bending normal stress. However, here we're looking at the welded joints. Bending normal stress, we're looking at welded. Remember the conservative model. What did we see? We actually explode on the cross section, which is the throat area. We explode basically the shear force. Basically, you forget about normal force. Just concentrate, basically explode the shear force. There's only shear force on the cross section, the throat area. So we don't call it bending normal stress anymore. So what do we call it? We're going to call it bending shear, okay, in this particular case. Yeah, it's a little awkward. We call it bending shear. But the formula-wise, it's still the same thing. So that's going to be our secondary shear. So let's say if I look at this location here, and what will be the, if I call it bending normal stress, right? If I call it bending normal stress, what direction would that go? The bending normal stress is caused by the bending moment, and bending moment is F times the distance, and that bending normal stress will be M times the distance from there to the center, and divided by the second moment of area I, right? So that direction will go, basically will go this way, right? Will go this way. That's the bending normal stress, right? So it still go that direction, and the way to calculate is still the same thing, but we call it a tau double prime secondary shear, and secondary shear we call that bending shear. Okay, yeah. It's just to be consistent with the conservative model that we're using there. Okay, everything on the throat area is a shear stress. Okay, and so tau double prime will be M times R over I, right? M times R over I. Okay, yeah. So technically, when you calculate the R, so technically what you would do is you would find the vertical distance from here to the center, right? To the center line here. So if this, let's say if this is a D at here, okay? If this is a D, then you would probably have to add a little bit distance at this location at here, right? At this location. But however, okay, that distance in general will be very small compared to this D at here. So in our calculation, we can, to simplify that, we can actually neglect that small distance there. We can just use the D, okay, basically just the distance half of what this member at here is, all right? Yeah, so you can just use the D there, okay, then divided by the I, okay? The I at here represent, okay, I is the second moment of area, okay, for the weld group, okay, for the weld, okay. For the weld, meaning here's the weld here. So what's the geometry? What does the geometry look like for the weld, right? Is it two horizontal bar? Is it a rectangular, or is it a circular, right? That's basically the geometry, and the geometry determines this I at here, okay? Yeah. And of course, m is f times the distance. So m, in that case, m times e for this notation and here, right? Yeah. Now I'll show you how to calculate I, but once you have a tau prime and tau double prime, then for this case here, they are always perpendicular to each other. Then the combined shear stress, which is the resultant shear stress, is going to be what? Tau equal to tau prime square plus tau double prime square, right? Okay, yeah. So that's the idea to how you would find the shear stress in the weld group, okay? When the F is out of plane with the weld group at here, okay? Yeah. Okay. So now the question is how to find I. So what we do is we use table 9-2, okay, 9-2 here. So table 9-2 looks like this one and here. Okay, so this is 9-2, just a snapshot of part of 9-2. I think there are a few more geometries there, but the way to use this 9-2 are very similar to the way to use 9-1. So the weld geometry given here is the unitless basic quantity here. Okay, it's unitless. So this straight line here just represent unitless for across the area, the throat area. Okay, across the throat area, and it's a straight line. Then the I here, they call it IU, so they call it unit second moment of area, right? Then when you calculate I, so what you do is 707H. Okay. So because when you have a, let's say, triangle here, and if this is H, the throat area is how much? It's this T at here, right? It's the T. And it's 45 degrees always, so T equal to 0.707H. Okay, so the T value times this unitless quantity give you this I value here. Okay, so this is IU at here. Okay, IU. If you have a two vertical bar, it'll be this. Two horizontal bar is this. So you got to be careful. Two vertical bar now has a different I now, right? In the previous case, when it's a value of polar moment of area, the two horizontal ones are actually the same thing as the two vertical ones, right? Yeah. Okay. And the area of the throat area, that's how you calculate. That's also given here. And then the average, the centroid location is also given right here. Okay. Yeah. So most important, I think, is to know how to calculate the I properly. Okay. Yeah.
Can you just explain the diagrams on the side of the table one more time?
Which diagram?
Sure, like how you would select.
This one?
In the table 9-2. Yeah. On the weld, like the little diagrams where it has G and D and everything.
G and
like how do we select which one?
What is actually a diagram of? Like what is it showing?
The weld column? Those
Yeah.
little...
Oh, this one here.
Yeah.
Yeah.
Oh, this is the shape of the weld, the geometry of the weld here. Say for example, right? If I have this one here, so what does that mean? That means I'll draw you a 3D case study here. So let's say this is a one base member at here. Okay. What was that? Okay, if this one base member, and then let's say I'm going to weld. I'm going to weld a shape like this. I'm going to weld something like this onto this member. Is that okay, right? So weld this thing onto this base member here, right? So how do you do the weld? You can do the weld, for example, you just weld it over here and over the other side there, right? And then you have a force probably applied at this location. So basically, what's the weld group now? It's 2 vertical bars, and that's this one here. Right? So it's a comparison between the geometry at here with the force F, right? With the force F. Okay. So ultimately, it's the F generates bending moment, and you learn that mechanics of material. This is the geometry. Then maybe your geometry is just like this. Then you have bending moment acting on this cross-section area. Make sense, right? So if you have, in this case here, okay, like what I draw here, right? Like what I draw here. And basically, where's that weld? The weld is actually where? Here, 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 and here, 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 right? Yeah. So the geometry here compared to the F, this is the geometry, and this is the F at here, right? And the F will cause a bending moment M on this geometry, okay, on this cross section. And at the same time, you have a vertical force, shear force F at here. Okay, so that's where that tau prime, this we call tau double prime on the weld group.
So the first one there was just a single bar that's just welded on one side.
Which one?
In the table 9-2.
Oh, the one bar. Yeah, this one just one bar, maybe this side or maybe that side there, right? Yeah. Yeah, the one bar is, well, if this one side there, technically speaking, you can have if there's a distance between, location F and there should be another torque, right, on it. But I guess if just one bar like this, then technically speaking, the one bar should be somehow centered here, right? But I guess it's not going to be used on this geometry, on the welding of this bar and the member like this. Okay, yeah. Maybe it's going to be a very thin. Who knows? Anyway, yeah, right? Yeah, you can imagine, but okay, yeah.
So does that only work for straight line welds then, or does that table also have like curved welds and everything?
This is not a straight line weld. This is a fillet weld. Yeah. So basically, it's going to be, if let's say you have a section, cross section here. You have this section here, so that shape should be a triangle, right? Should be a triangle like this. Yeah, so it's a fillet.
Instead of like having a square bar, if you have like a round bar welded to that shape.
Yeah, if it's a weld bar, if it's a round bar, you could still have this a triangle shape, right? You can still have a triangle shape. I'm not good at drawing now.
No, but like there's no, obviously in that table 9-2, there's nothing for like a round.
Oh, there should be. I didn't include everything in here. Yeah, if it's a textbook should have it on there. Yeah. Well, somebody can confirm that to me. Yeah. I think there's a couple more at here. Yeah. Good. Yeah, very good. So now the next question is, let's analyze the welded joints. Okay. And particularly the fillet kind of weld. Now, we actually already calculated the stress. So in order to do the analysis, then all we need is basically the strength now, right? So then we can compare the stress with the strength. Okay. Yeah. So first thing we need to understand is, okay, when we do analysis of a joint, make sure you understand which portion you're analyzing here. So this diagram, this little diagram here shows you, if I have a fillet weld here, so technically speaking, there are three portions, actually just two portions of particular interest. One is somewhere in the middle of the welds here, and the other one is this location or this location. If you recall that this two pink location here, we call the fusion location, right? Fusion. So that's the location generally has a mixture of the filler material and the base metal there. Okay, yeah. But really, even at this filler, the middle location, the blue color location right here, it's still a mixture of base metal and the filler material. Okay, so when you analyze the welded joint, watch the sentence of this question here. Sometimes the kind of question is, okay, analyze the safety of the welded metal. Of the weld metal. So what does this mean is, it means just look at the filler material that you picked. Is it going to be safe or not? Okay. So that's one way to look at. They don't want you to look at the base material. You know, you pick the filler material, and the filler material has a certain strength. So, and then based on the loading, you have certain stress. So, is the filler material a proper selection? Right. That's basically one way of analyzing. And the second one here is they call it is analyze the welded joint, the whole joint. Okay. So analyze the safety of the whole joint. Okay. Now, if this is the case, then when you do the analysis, as I'm going to show you next, you're going to have to also take the material of the base metal into consideration, as well as the filler material. Okay, as well as the filler material, right? So this one here, so just the filler material matters. Okay, and this one here, so all materials, okay, base material plus, I'll just put it here, base material, base metal, and okay, filler material. Okay, so we have to take both cases into consideration here. All right, yeah. Okay, so now let's look at individually what do we mean by filler material strengths. Okay, and base metal material strengths. That's okay. That can be easily looked up from the tables here, right? Yeah. So here is a table. I'm going to show you it here. So this table 9-3. Okay, this is table 9-3 right here. Now this is our guideline regarding the filler material property. Okay, filler material property. So when you pick an electrode, okay, and those are basically designations by AWS, American Welding Society. It started with a E60 or 70 and then followed by two other digits there. So the first two digits, what it tells you is it's roughly basically indication of the tensile strength at here. Okay, the tensile strength. And this column tells you the yield strength at here. Right? So it basically tells you the SUT, and this gives you the SY at here. Okay, so this is table 9-5. Okay, 9-5. So in general, the filler material need to be picked to match the base material or the parent material. Okay, so there is, if you look into the standard given by AWS, there's always some kind of stress state table that you should stick to in terms of picking the right electrode or the right filler material. Okay. Yeah. So filler material okay, needs to match, okay, base metal. Okay, yeah. Okay, yeah. So now the next question is, what will be the strengths? Okay, how do we get the strengths at this welded joint? Okay, so strengths. Okay, so the guideline for calculating the strengths is this table 9-4. So there are many tables. So 9-4 is this one here. So we basically make use of this table. Okay, 9-4. So let me show you how to make use of this table here. So this table, okay, give you different kind of basically different kind of a loaded joint here. If it's a tension joint, or bearing joint, bending joint, or simply compressed joint, or shear. So this one here is actually for fillet. That's kind of our case study here. Okay, kind of our case. So this value here basically saying 0.30 SUT. That's the permissible stress. Remember we said we find the shear stress now. We want to compare with a strength, right? We basically want to compare with allowable value. So this is the value we're going to compare with. Okay, 0.30 SUT. However, there's another one you guys be careful here. At the bottom of the footnote here, okay, there's another one that says the shear stress on the base metal should not exceed 0.4 SY of base metal. So our guidelines actually there are two things. Okay, just remember there are two. There's 1.30 SUT. There's another one 0.40 SY. Okay, 0.40 SY. Technically, this table, okay, if you look at the textbook, they use the table on the welded metal, on the filler material. But we're going to use the table actually. If we're going to analyze the welded joint, our SUT-SY is not just the SUT-SY for the filler material. It's also going to be the material property for the base metal. Okay, for the base metal. So here's what you can use. This is the way how you use this. How you use this one here. Okay, so because we're comparing the stress, we're comparing the shear stress, then the strengths we're looking at here is I'll use SSY, okay, as this strength value, and so basically it's the shear strength, okay, or it's a permissible shear strength. So this SSY, okay, what you do is, okay, or we can also call that, okay, tau allowable, okay. So that's going to be equal to mean value, okay, 0.3 SUT and 0.4 SY, okay, and 0.4 SY, okay. So if we're going to analyze the whole weld joint, okay, so everywhere. We want to make sure the safety everywhere at the welded joint, not just the weld group, not just the fusing area, okay. So we're going to calculate the strength is this. Now the SUT-SY, okay, so when you do that, the SUT-SY, SUT is going to be the minimum value of the electrode, okay, and perimaterial, so basically base metal, maybe perimaterial 1 or maybe perimaterial 2, right? Maybe you have 2 perimaterial. Okay. Okay, so that's your SUT, right? That's your SUT. SY is the same thing. So SY is also going to be the mean value, okay, of this. So where do I get this SUT for the electrode? That's the table 9-2. Okay, 9-2. This table. Oh no, sorry, 9-5. Okay, from here. Okay, to get SUT-SY for the electrode. So where do we get the perimaterial SUT and SY? You go to the table, right, from the appendix. Okay. So that's how you get SUT-SY. Then you plug it here. the mean value of 0.3 SUT and 0.4 SY is going to be the allowable or the so-called permissible stress. Then you compare that with the calculated tau value, then you can get a safety factor. Okay? Yeah. So this is the typical process in terms of analyze the joint here. Okay, we'll illustrate this thing through an example. Okay. Any questions so far? Okay. Yeah. So this example is very similar to the example that we did from previous lecture. Okay. So just want to, but I'll change the number a little bit. Okay. I'll use an in-plane example. Okay. So we have 2-inch over here and 2-inch at here and 6-inch at here. 5/16. Not this way. Okay, so that's the symbol like this. Okay. So suppose that we're using this the electrode we used for the weld is E7010. Okay, and this is the bar here. This is the bar 1. Let's see, this is the bar 2. And for bar 1 is hot rod 1020, and bar 2 is hot rod 1015. Okay. Right. Now the question here is, what will be a suitable force F? What's the allowable load? Okay, what will be allowable load F based on this given informations? Okay, so let's look at this question in here. So that's a typical question that can appear in the final exam here in terms of the welded joints. Okay. Okay. So first, what we need to do is we need to calculate. Okay. F we don't know, but we can calculate the stress. Okay, in terms of F. Right. I think that actually we did a little bit similar one, but in the previous lecture, I think I used 3 at here, right? I used a 3, yeah. So first, let's calculate this the stress. Okay. So draw the geometry of the weld first. Okay. It's 2 horizontal bar, as indicated, because the 2 triangle here, meaning you have weld. So when the arrow side, this is arrow side, that's the other side, right? This is the other side. So you got 2 basically symmetric weld. And 5/16, remember what that is?
H.
That's right, that's H. So you need that information, okay? Yeah. Okay, so this is the shape right here. Now you can label the geometry of the shape, and this portion, in this case it's in plane, so we should make use of a table what? Table 9-1. Okay, 9-1. And if you look at the 9-1, 9-1 doesn't have two horizontal, but as I said, this is the one you use, right? This is the one you use. So the geometry at here, this is a D, this is a B. So basically, this is a D here, and this is a B here. Okay, yeah. In this case, they're all 2, so lucky enough you won't make a mistake if this is the case, right? But if they're different, then you got to be careful. Make sure you got the right number values for D and B, though.
D is always the bigger value then,
D, not necessary.
right? They're not equal numbers.
You mean D's value? D is the length of the welds here, right?
Oh, okay.
So B is the gap between these two. So not necessarily D is always greater than B, though, huh?
Okay.
Yeah. So for example, if I put 3 at here, 2 at here, so D would be 2, B would be 3, right? Yeah. Okay, so centroid, that's kind of easy because it's symmetric, so just put the centroid here. Okay. Then critical location, apparently it will be location right here, right? It will be right here. Okay. So at this location, you have 2 different kind of stress. One is the primary shear, tau prime. Okay. The other is the secondary shear, tau double prime. But tau double prime, remember, I don't calculate tau double prime directly. So we calculate what? We calculate the tau x double prime and the tau y double prime, right? The 2 component, 2 decomposed component of this tau double prime. So tau x double prime is this, and tau y double prime is going to be this. Okay, this. All right. So now let's calculate each one of them. Okay. So how do we calculate each one of them? And your tau prime is equal to F over A. Okay. F we don't know, we keep it F. And A is the total throat area. So if you look at the table 9-1, what would that be? That's 1.414 times H times what? Times D, right? Times D. Okay? Yeah. H we have it already. So F over this. Okay? F over this. H is 5 over 16, and D is 2. Okay, so simplify that. 1.13 F KSI. Okay. Yeah, for now I use the KSI. You can also use the PSI, but I think just for the easy of a calculation in terms of the calculation there, okay? Because in the material property, most of them will be KSI, right? So we use KSI here. So that's tau prime. Tau x prime. Tau x prime is caused by the torque, and torque is given by, I'll write it down the whole formula. So that's T times R over J, right? And T equal to F times the total length to the centroid. So centroid is here. Then the total length in this case is F times 6 plus 1, right? Plus 1. Yeah, that's kind of easy because it's 2 divided by 1. If you really want accurate ones, you actually have to look at the table, just in case the geometry is not symmetric, right? So you look at the table here, basically where this X bar is, okay? Where the X bar. So that gives you the exact information though, okay? So F times 7. And R, because we're looking for the X in this direction, that'll be basically this distance, right? This distance. So that's B over 2, okay, that's 1. And J is 0.707 H times JU. And JU, that's from where? Table 9-1, it's this quantity here, okay, this quantity. So JU equal to D, 3B squared plus D squared over 6. So JU equal to D, okay, 3b squared plus d squared over 6. So this is where the importance of getting the right value for the d and the b. Okay? If you don't get a right value d and b, your GU will be wrong. GU will be wrong, then everything else will be wrong. So in this case, d and b are all 2. So then plugging the numbers. Okay, it's inch cube. Okay, this is inch cube unit. Okay, unit is inch cube. So once you times h, it'll become inch to the power 4, and that's the standard unit for the G. Okay, so plugging everything here, calculate tau x double prime in terms of the F, and that give us 5.93 F KSI. Okay, like this. Was that good? Then tau y double prime. So if you look at this one here, tau x double prime, this is the R here, right? When you calculate tau y double prime, you use which one now? This is the R. From here to here is the R. But because the geometry, this R is actually same as this one. So basically the tau y double prime the same as tau x double prime. Okay, the same with this. Okay, so once we now have everything, then the total shear stress is tau prime plus tau y prime double prime square and tau x double prime square. So plug every numbers, every values expression in it, and then calculate the tau. We got 9.22 F KSI. Okay. We want to calculate the allowable load F, so we need to compare the tau with the allowable stress or permissible stress or the strength. So then the next part is to calculate the permissible stress. So the formula that we use, the tau allowable, the formula we use is mean as before, SUT 0.4 SY. Okay, 0.4 SY. And SUT are based on the mean value of 3 different material in this case, right? So what are 3 different material? Because there's bar 1, bar 2, and there's a filler material. So the 3 different ones. Okay? Yeah. Same thing for the SY. It should also be based on the 3 different material here. So best practice is list the properties of all the 3 material here. So for electrode, okay, which is E7010, okay, E7010. So if you look at the table, okay, E7010, what's the SUT? As I said, the 70 basically tells you SUT is 70, right? But you need SY, and that's 57 at here. Okay, so SUT is 70, SY is 57. So unit is KSI. Okay, and then bar 1 is 1020 hot roll. Now that you had to look at the table 8-20. Okay, 8-20. So for 1020, my SUT is 55 and SY 30. For 1015, SUT is 70, SY is 50. Oh no, sorry. 50 at here. 27.5 here. Okay. Okay, so that's the material property at here. So plugging this formula, right? Plugging this formula. So my SUT, first of all, before you execute, SUT is the mean value of which one? Of the 3 here. So apparently it's 50, right? Was that right? Yeah. And then the mean value of these 3. Oh, I guess I don't need to do this anymore. So you can just look at it. So this is 50, and SY will be 27.5. So then plug it into here. Then you calculate your total allowable. Is the mean value between that two. So calculate this 0.3 by 50, 0.4 by 27.5. So what do we get? We get 15, 11. So apparently 11 is smaller. So permissible stress will take it as 11. Okay, take it 11. 11 is the permissible stress. The current stress is 9.22 F. Then the maximum allowable load will be 11 over 9.22. Equal 1.19 kip. So 1.19. That 1 kip is 1,000 pound force. So that's 1,190 pound force. Okay. Yeah. Is that clear? Yeah. So this is a typical process for getting this. There is an basically alternative way of basically making use of this process is this. So just think about this, what happens here, right? So now you have a weld group here, and it doesn't tell you the leg size H. Okay, so give you the H at here, and this one is gonna give you, okay, and the material gonna give you. And then it's going to ask you is, what will be a proper leg size for the weld joint, okay, for the weld. Is that good? So, basically same calculation, right? Now the only unknown is H. So in the end, you calculate the H value, right? You calculate H value. The only catch at the end is, when you calculate H value, you calculate H, and then you probably will get certain kind of decimal numbers, point, who knows, maybe 0.22, for example, right? 0.22. So when you choose the H, it's like a design question. Then you choose what? You choose the next legitimate fraction size, the nominal size in fraction. So I would choose a quarter, right? So that's kind of the case there, right? Yeah. So I think. I'm not sure if I have I think one of the tutorial question probably is like that. Yeah.
Oh, I was wondering, do we ever consider the quality of the weld?
Quality? No. Yeah. Quality definitely is an issue there. Yeah, but we're focusing on the technical calculation part. Yeah. Okay. We'll leave that to the proficiency of the welder. Yeah, that's the quality there. Okay. Yeah. So any questions? All good? So that's basically the kind of question for the weld, okay, for the welded joints. If we don't have a question, I have one more topic to cover, which is the spring. Okay, mechanical spring. Okay, so let me show you where we are in terms of spring. Okay. So we've been going up and down at here. So now spring is over here, right? Yeah. So as you can see, we're not going to be able to cover every one of it. We cover most of the trees that are here, most of the branches. So spring is here. Okay. Yeah. So whatever you use a spring, spring has wild applications. One of the application is in automobile. You have this suspension spring, okay, at the wheel. Okay, when the wheel goes over the bump, the spring will be compressed, and as it go after a cross the bump, then the spring will release the energy. Basically, spring is the component that stores and releases energy, right? Yeah. There are different kinds of spring. Okay. Most commonly seen spring, this one here is called helical compression spring. Basically, that spring should be used only in compressive kind of a situation, right? You don't use the helical compression spring in a tension situation. But this one is the helical tension, so you use that in a tension kind of situation, right? Yeah. And this is a torsional spring. If you have pins or snap things, on the magnet on the refrigerator, you see that right in the mechanism there. And this is a leaf spring. Most of the truck heavy loaded automobile, you see that as a suspension kind of spring there. This is a washer, but it's called a Belleville washer. So that's also actually kind of spring kind of mechanism, basically. It gives you the kind of friction. Basically, they use it as a kind of a locker, basically. Okay, yeah. So some other examples: suspension springs. So this is the leaf spring there. Okay, and this is the coil, the helical compressive kind of spring used in the engine. Okay, controlling the valves opening and closing. Right. So this is a crankshaft, and this is the cam. So when the crankshaft rotates, the cam will push the push rod, and then basically will the rocker arm will push down this valve, and then in this opening. Then when it's closing, the spring basically will release the energy and then close this valve at here, right? Okay, yeah. Okay, so what we need to know is I need you to know a couple of terminologies that are here. Most of the terminologies actually are pretty familiar to us, because when we're learning thread, when you learn screw, we said the screw is basically a helical kind of a curve, right, around a metal bar. So spring, the same thing. Spring is a helical curve, basically parametric equation. It's a helix. Okay. So what's the important parameter then? First, it's the distance between two adjacent coil. Okay, this P, that's called a pitch. Okay, so P is the distance between two adjacent coil. Basically, you take from this center to the next center. Okay, that's the P. And there's another one called total length. L is called the free length. Free length, basically, before you apply any force, what's the total length of the spring? We use LO to represent that. Now, if you apply the force enough, then the spring will completely close itself. Okay, and that's called LS. So that's give you the solid strength LS. Okay, yeah. So those are easy to understand here. Okay, mean coil diameter is also easy. So that's the diameter from the center right here, okay, to the center over here. That's the mean diameter, capital D. Okay, capital D. And of course, F is the external load. Helix angle. Yeah, I think the helix angle should be this one, but anyway. So helix angle basically is the angle representing, this is a helix between the helical curve and the vertical axis of a rotation, right? That's the helix angle here. So as a matter of fact, we're not going to use this one here. Wire diameter, that's also important one here. That's basically the diameter of this wire at here. Okay, this is wire. Okay, so I'll leave the last three at here as the most important one here. That's actually the most confusing part. Okay, NT, total number of coils. This is actually not bad. Total number of coils. So what does it mean? What does that mean? Basically, you start to count, right? 1, 2, 3. So how many turns does a spring have? That's the total number of coils. Okay? Yeah. end coils, I'll show you next. So this kind of spring is basically a plain spring. You know, basically after manufacturing, just cut it off, and that's it, right? That's basically called plain spring. And you probably will see some spring that have a different kind of ending at here and here. Okay, so that's basically using this symbol NE to represent how the coil ends. Okay, how the coil ends. So for example, in the next, I'll show you in the diagram here. You see this one. This is a plane. See, this one here is called a square here. Basically, the ending, right? The ending at here was pressed down there, okay, and then you have a closed distance between here and here, okay, between these two part of the two coils at here. Okay, that's called squared. And this one here is called grounded. So essentially, make sure ground is not the same as square though, huh? Grounded basically means this is the plain one. You know, you don't want this one to keep going. You want to have a better contact between the spring and the surface or the member it's in support, right? So what do? We basically cut off, okay, part of this, cut off part of the top and the bottom here, okay? So make it flat. So that's what we call grounded here, okay? But grounded doesn't mean like this one, okay? Grounded means this, you still have the regular gap like the pitch as they are, right? But not like this. This is closed. Okay, so sometimes when we say squared, we also call it closed one, okay, or closed spring. Okay. Now, most commonly thing is probably say is square and ground. Basically, after you squared it, then you cut off here, okay, or ground the top portion here, and that'll become this one here. That's become ground and squared. Okay, ground squared. Right. So each one of this kind of ending type give you this NE value. So they could be 0, could be 1, or could be 2. And table 10-1 is where you should look up to. Okay, this is where you can get the information. Okay, so the last one is the NA. It's called number of active coil. So that's the keyword. Number of active coil. Okay, number of active coil. So active coil basically means it's the coil that's not closed. So if a coil, if two adjacent, the coil is closed or touching the adjacent one, then that should not be counted as an active coil. Okay, as an active coil. Is that good? So getting the right value for the NA. That's the next exercise. Okay, I'll show you, and which is very important. You need to have that capability though, because NA value is wrong, everything else is wrong. Okay, yeah. So active coil, I'll just write it here, is the coil that are free to deflect, okay, under load. Okay, that's the active coil. So basically, active coil is the coil is kind of coil makes what a spring. Okay, yeah. So how do I count NA? How do I get NT and everything? Basically, NA very important. Okay, very important. Watch carefully about how to count NA. So let's look at a couple of examples here, okay? And I have an example. Let's start from the simple ones there. Okay, so let's look at the plain one. For the plain one, the NA and NT, remember NT is? NT is the total number of coil, right? NT is the total number of coil. So the NA, NT will be the same thing, okay? It will be the same thing. So how do I count the count coils then? Okay, so I mean, how do I count the coils? Well, just look at this one here. Can you tell me how many coils does this spring have? So suppose started here and ended here. Let me count it. 1, 2, 3, 4, 5, 6, 7, 8, right? I would say 8. Why the 8? See, this is from here, one turn is one coil. That's 1, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay? So that should be 8 at here. It's a plain one. If you look at the table 10, is that table 10? Dash 1. Yeah. The NE is 0. Okay, the NE is 0. Then you can easily calculate what's the free length, what's the solid length, using these formulas at here. Okay, using the formula. And the pitch can also be calculated. And pitch maybe is given. Who knows, right? Yeah. But those are the formulas you can make use of at here. Okay, so LO equal to PNA plus D. Okay. So suppose that I'll tell you this one here. Pitch is 5 millimeter. The wire diameter is 3 millimeter. So that gives us LO. The free length is 43 millimeter. And LS, the solid length, the formula from the table is a DNT plus 1. That's 27 millimeter. Okay, 27 millimeter. Okay, so this is easy one. Okay, this is easy one. So next one here. So let's just suppose I didn't tell you. Okay, probably in the question I'll just give you a spring without telling you anything. What kind of spring that is? Just give you the spring there, right? So you have to identify what kind of spring this is. So let's say this one here, and you see it already. So this must be, there's no grounding here, right? No grounding here. So this is actually just a square one, huh? It's closed. Okay, it's closed, a square. If the square one, first, can you count how many number of turns does this one have? 7. So starting here, 1, 2, 3, 4, 5, 6, 7, 8, right? That should be 8. So that's the total number of coil. Okay, total number of coil. This is very important, okay? Because every year I have so many. Because this is the last lecture. Generally, what happens is people will not spend too much time before the exam on this last lecture. And when it comes to spring question, they count NT wrong, and they get the wrong spring. The whole 20 points question is basically all wrong, right? Okay. So if NT is 8, so then the next step is you identify what kind of spring this is. So let's say you identify the square. If it's a square, then you come back to the table here. The NE value is 2, right? It's 2. And the NA value, NA is the total. NA is the total number of active coil. How do I get that? It's NT minus 2, right? It's NT minus 2. Okay, so that should be 6. And or if you forgot a formula, if you panicked, don't know where to find NA, so use a common sense, right? Total number of active coil. Basically, you don't count from here to here. You don't count that as one number of coil anymore. Because why? Because this here, there's no room for deflection, right? No room for deflection. So you can start from here, right? 1, 2, 3, 4, 5, 6. Okay, that's NA there. Okay, that's NA. Okay. Is that good? So let me write it here first. Okay, identify Okay, the type of spring. Basically, based on the ending. Okay, based on ending type. There are only three different ending: plain, square, or grounded, and a combine of square and grounded, right? Yeah, grounded is easy to identify. If it's flat, then it's ground, right? Yeah. Square meaning there's a closed gap, right? Closed gap between for the last number of coil. Yeah.
Can one end be squared and the other end not be squared in any cases?
Yeah, you could. Yeah, definitely. You could. But if that's the case, right, you actually can't use the table anymore. So there is a limitation for the table. You know, as a mechanical engineer, you could have any different kind of situation. But this table, I think, is for most commonly seeing situation like this one here. Yeah. Okay. Yeah. So identify the type based on this. Okay. Obtain the NA. Okay. Obtain the NA by counting NT correctly. Yeah. So know how to count the coil. That's one coil. Okay. One turns one coil. Technically speaking, what we see here, right? We see here the all integer number for coils here, right? So technically speaking, you could have basically a square or ground starting from a quarter or a half turn. Okay, technically speaking. Okay, so this table. So there's a restriction here. This table I don't think that you should use that table for every kind of a situation. Okay, yeah. But if in the question given to you, and you shouldn't worry too much about that. Okay, so just make sure you know how to count properly, and you know how to use the table to find the right value of NA. Is that good? Okay. Yeah. So now next is stress. What kind of stress do we see in the spring? Okay, it's actually quite common, very simple. So suppose the spring is under a load F at here. Okay, so there are a whole bunch of other coils here. So then what I do is let's cut a cross section here. We look at the cross section. Okay, just at the cross section here, what kind of stress exists at this cross section? Free body diagram. To balance this F, you need an F upwards. You also need a torque to balance F, right? So the F will cause the torque at this location, and the distance is capital D over 2, right? So two things to balance that. Then at this circular location here, then you would have two kind of stress. One is caused by the F. Basically, if you cut a cross section on the other side, you will have a shear stress, right, by the shear force. You can also have a shear stress caused by the torque, right? Caused by the torque. I think it'll be this way, right? It'll be this way. Okay. So basically, you would have at this location, it'll be superimposed together, two stresses imposed together, right? So one of the stress, okay, is tau equal to F over A. Okay, so let's call it tau 1. And A is a cross-section area. So cross-section, the wire has a diameter D. So area is pi D squared over 4. So the 4 jumped to the top there. That's tau 1. And tau 2 is a stress caused by the torque. And that's TR over J. Okay? And if you plug everything, that's 8F capital D over pi D cube. Okay? Pi D cube. So together, these two, add them algebraically, so the tau will equal to 4f over pi d squared plus 8f d over pi d cubed. Okay, so that's the stress, combined stress together on the cross section. And conventionally, we don't write it like this. We define ourselves as C as a ratio between the capital D and a small d. Okay, the ratio is called spring index. Okay, this is called a spring index. Based on this C, my combined stress tau can be rewritten as this one, as Ks 8f capital D over pi d cubed. And the Ks equal to 2c plus 1 over 2c. Okay, Ks. Okay, that's it. That's the stress on the cross section of the spring there, okay, due to the loading F. Okay. Then the next thing is we noticed that some researchers noticed the way to derive this one here are based on assumption, basically. So when you use this formula, okay, when you use this formula here, that formula apply to straight wire or straight bar, okay. But when it comes to curved bar, and this is the case, right? The spring, it's not a straight one; it's a curved, right? Everywhere is curved. So this formula does not correctly describe the shear stress, okay, distribution, basically. So here's the diagram, okay, showing here. For a straight one, that's good, like this, right? But for a curved one, as you can see, one side is bigger and the other side is slightly smaller. Okay, so what do we do is basically there is a whole bunch of basically research here to modify this formula here. Okay, to modify the formula, better depicting the stress distribution, okay, on the curved wire at here. So there is final verification of final here. I'm going to use, there are different modifications here. So I'll use KB here. It will use this, so-called KB 8FD over pi D. So this is what we're going to use here, okay? So you compare this to original KS. So now I'm going to use KB. And KB, because why is it called PB? Because this is from a researcher which is called the Bergenstresser. Okay, it's from a guy called Bergstresser. So KB is basically something called Bergstresser factor. Now, this is the formula we're going to use. Okay, so this is the formula we're going to use to calculate the stress on the spring. Is that good? Okay. And we're almost done there. Basically, I'll stop here. Once we have the spring, and the next we try to find the strengths. And then we compare the two, and we'll know whether it's safe or not. Right? So next lecture we'll talk strengths and then one example. And then we'll do a quick review on the whole lectures. Okay?